So horizontal circles, I'd like you to imagine that you're in a car turning a corner. This is a top view. What's the direction of your acceleration? What is the direction of your acceleration? Hopefully by now I've convinced you of this. Which way are we accelerating? So let's all of us draw a little arrow pointing that way. Let's call that A. What's the direction of the net force acting on you then? Let's draw another arrow. Call that FC. This isn't a free body diagram because FC doesn't appear on my free body diagram. I'm just labeling directions right now. By the way, although I didn't ask this question, what direction is our velocity? The velocity would always be tangent to the radius. The velocity would be tangent to the radius. Our velocity is always at 90 degrees to wherever to the center of the circle, wherever the radius is. Acceleration points inwards. This is a great multiple choice question. In fact, I'm willing to bet you'll see a similar question to this on the test. However, Maddie, I want to teach you how to answer it. Never, these 2-column chart questions, never read across, always read down. Acceleration, yes, yes, no, no. Net force, yes, no, yes, no. Then zoom out and it's obvious what the correct answer is. By doing it that way, Nina, you're only having to track one concept at a time instead of having to track 2 concepts in your head at a time. That's when students make silly mistakes. It's preventable. Explain your answer. I think we spent 2 days explaining your answer, so I'm not going to freak about that. Instead, there's something called a centrifuge. I don't like the name because a centrifuge is named after with an F, centrifugal force, which is not a force, it's inertia, but whatever, they're called centrifuges. They're little test tube devices that spin really fast, and you spin it fast enough, you can separate different substances, you can break cells apart, you can separate blood plasma from hemoglobin or whatever. So a test tube rotates with a period of 9.9 times 10 to the negative 4 seconds. That's pretty fast. That's a very small number. What's the centripetal force on an amoeba at the bottom of the test tube? The bottom of the test tube rotates in a circle with a radius of 0.15 meters. What's this question want me to find, Maddie? Well, FC equals MAC, I guess is where I would start. We're going to get more difficult, but this is actually just a straight plug and chug because I have 2 expressions for AC. I have V squared over R, and I have 4 pi squared R over T squared. Maddie, which one am I going to use here? They gave me V. Which one am I going to use here? They gave me the period. Ah, yeah, that one. And by the way, the other thing you could do, it'll be silly because you're adding extra steps. You could only use this one, but then you could always say, I know that V equals 2 pi R over the period. You could find how fast it's spinning every time first, and then go to here, and then go to here. But what we did to get this equation is we combined these 2. So why not use the combined one? We're going to get this. M4 pi squared R over T squared. The biggest mistake kids make with this equation, Maddie, is they write FC equals 4 pi squared R over T squared. Because it's such a complicated expression, they forget you've just said force is acceleration. That's not true. F equals what? MA. So it's going to be 1.8 times 10 to the negative 9. 4 pi squared 0.15 all divided by 9.9 times 10 to the negative 4 squared. I said to you we're going to be getting to some fairly complicated calculator work. Please, every one of you, try typing this in. Yep. I got 0.0109. If I round off to 3 sig figs, 1.09 times 10 to the negative 2. Anybody else? I see one thumbs up. Yeah. Some of you, I've seen the odd software that doesn't let you do a pi squared. It makes you do pi times pi. So if you got an error, you might have to, on your calculator, go pi times pi. Later on this year, we'll find some of your calculators have another weird pi glitch. Is that right? Yes? 1.09 times 10 to the negative 2 newtons. That, to me, Michael, was straight plug and chug. I gave you all the information and I said, hey, find the force. Okay. Let's go a little further. I like example 2. I like example 2. I like example 2. I like example 2. Example 2 is a nice question. A car is approaching a circular turn that has a radius of 60 meters. If the coefficient of friction between the car and the pavement is 0.45, what's the maximum speed that the car can safely travel through the turn? You know what this is a job for? Nina? It is a job for a free body diagram, but there's a problem. Which free body diagram? Don't write this down. Don't write this down. A lot of students don't write this down. Sean, you with me? Alan, you with me? Because you're staring at something. I want you back here. A lot of students go top view. Don't write this down. So they think there's the road. They draw a car. What are the forces acting on this car? Get the obvious one. Which way? Into, oh. How would I show that? It's going right into the paper. And a normal force right out of the paper. Top view is not the best way to draw this. A much better way to draw this, you can write this down if you want to, is front view. I'm actually not going to represent the car as a dot. I'm actually going to draw the car a little bit. So here is the pavement, and right here is the center of the circle. We're going to come out of the page towards us. We're going around the circle, coming out of the page and going around like that. And here is Mr. Dueck's totally impressive drawing of a car coming out of the page towards us. Mr. Dueck draws 2 tires. Then Mr. Dueck draws the grille. There's the headlights. And there's the roof of the car. Now, it's a terrible drawing, but I want you to know it's a better free body diagram because what are the forces acting on this car? Get the obvious one. Is the car sinking into the ground like quicksand? Is the car lifting into the air like Superman? What else? Normal force, same size as mg? What path is this car tracing out? Looking for where it means letter C. A circle. So where must my winning net force be pointing? Toward the... So I know there has to be a force pointing that way. It's not FC. FC never shows up on my free body diagram. The real question is, what force pushes a car around a circle? What? Ah! Friction. So for the car questions, Maddie, you don't have to draw the car picture. You can represent it with a dot. But what I am saying is your best view is the front view. Having it coming out of the page towards you is by far, I've played around with a bunch of, I tried side view, I tried 45, I tried top view. This is the clearest and easiest to draw. Who's winning? Vertically, it's a tie. Who's winning? What path are we tracing out? A circle. Where is the winning force pointing? Toward the... So we're going to say friction. Who's losing? It's a trick question. But a lot of people will want to put a force pointing that way because I feel like I'm getting pushed outwards. You're not. That's your body's own inertia. That's Newton's first kicking in. You want to keep going in a straight line at a steady speed. Don't put a force pointing that way. So who's losing? No one. That's going to equal MAC. friction is what times what? Mu times the normal force. That equals m. Maddie, which version of acceleration am I going to use? The one with the period or the one with the speed in it? What's this question asking me to find? Am I going to use the one with the period or the one with the speed in it? Okay, so in other words, what you're going to have to ask yourself every time is, does this question give me or ask for the speed? I'll use v squared over r. Does this question give me or ask for the period? I'll use 4 pi squared r over t squared. That's got to be another habit. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? Friction's the same size as the normal force? Oh, do you say m? Is that what you said? Oh, okay. Mu mg equals mv squared over r. Oh! Hey! Johnny, what do you notice? What? Do we have to build separate roads for semi-trucks and separate roads for middle trucks and separate roads for small cars and separate roads for motorcycles? Or are they all able to go around the same corners? They can all travel on the same roads? Really? You mean we didn't have to build completely different infrastructures for every different size mass vehicle? Wow, who would have thought that? Maddie, what are we trying to find? How would I get the V by itself? In fact, I think last day we got the square root of gur a couple of times. Here, square root of mu gur. So it's kind of a familiar friend almost. It tells me I probably did this correct. V is going to be the square root of mu gur. Yep. By the way, if you've ever been approaching a corner and you see a speed limit sign, do this corner at 40 kilometers per hour, or whatever, this is how they calculated it. They know the coefficient. Probably they're using the coefficient of wet pavement on a rainy day because that's their built-in safety margin because they know you're stupid drivers, right? It's going to be the square root of 0.45, 9.8, 60. What do you get? You get 16.3 times by 3.6. 60 kilometers per hour. This road here, this curve here, would be okay in a subdivision or even on the low heat. You wouldn't need to put a speed change sign. Cars could handle it okay. Although this is the maximum speed. If you'd hit it doing, you know what? They would tell you to slow down. At that speed, you would feel like your wheels were really close to slipping. You would be uncomfortable behind the steering wheel. You could feel it through your body that your car was just about to lose control. There's a great swing ride at Playland. It's called the Wave Swinger. The circular swings that you get in. I'm betting most of you have been on those at least once. So there's some great physics there. I want you to notice that even though the rope is at an angle, the circle that you're tracing out is a horizontal circle. An empty swing on an amusement park ride has a mass of 10 kilograms. If the swing has a kinetic energy of 460 joules, what's the centripetal force acting on this swing? Victor, what's this question asking me to find? My first thought is, oh, well, FC equals MAC. Maddie, am I going to use the one with the V or the one with the T in it? This one's a bit trickier. Do you see a V in this question anywhere? Do you see a period T in this question anywhere? What else did this question give me? What's the equation for kinetic energy? I'm going to use the one with the V in it. Okay? So I'm going to go here. And I'm going to pause. I got the mass, 10. I got R from the picture, 7. Over here, let's write down K E equals a half mv squared? Let's get, now I could start plugging in numbers, but I want to show you something kind of cool. I'm going to get the v squared by itself. I'm actually not going to get the v by itself. I'm going to get the v squared by itself because, James, there's a v squared over here, so why would I bother taking the square root when I'm going to square it when I put it back in anyways? James, how would I get the v squared by itself? What do I do with the m? I don't know what that means. Divide, and what do I do with this 2 times it to the top? And I would divide by the 1. Am I going to bother dividing by the 1? Is that going to change anything at all? Okay, so I get this. V squared equals twice the kinetic energy divided by the mass. And I'm going to go stick that in over here. I'm going to get the centripetal force is the mass over r. But what am I going to replace the v squared with? Twice the kinetic energy over m. Is that okay? Johnny? Huh? What do I notice? Really? How many of you have ever been on the Music Express ride before? The circular swings. Okay? Next time you're on there, look at an empty swing and look at a swing with a person in it. The empty swings do not swing way further out. Or the ones with the people in them don't go way down low. The angles are the same. It also means little kids and grown-ups can go on this amusement park ride and we don't have to specially modify anything. Doesn't matter which swing you go on. So it's going to be 2 times 460 divided by 7, which is what? 131 newtons. Direction towards the horizontal center, not along the rope, towards the center. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. A car can travel without slipping at a maximum speed of 32 meters per second in a circular path of radius 72 meters when the pavement is dry. When it rains, the coefficient of friction is reduced to half its original value, which is about accurate. What's the maximum safe speed of the car under this wet condition? I don't know. Any suggestions on how I might want to start? I think I'm going to do a free body diagram. In fact, I think I'm going to do the front view car one, except this time I'm just going to represent the car with a dot. But if you want to draw the wheels and the grille and the headlights and the roof, go ahead. But I'm going to do one more thing, William. I'm going to do a free body diagram right here, but I think I'm going to go like this. Dry, rain. I have a feeling. This is a guess. So here's the car going around a corner. I see some of you disappointed. Fine, I'll draw my artwork. There's the wheels. There's the grille. There's the headlights. There's the roof. Okay. What are the forces acting on this car? Get the obvious one. Gravity, you say. What else? Normal force. What else? Friction pointing which way? All right. It wants the maximum safe speed of the car when it's wet. So let's start over here where it's rainy. Who's winning? Friction. What's that going to... Who's losing? No one. What's that going to equal? M-A-C, pause. Maddie, am I going to use the one with the speed in it, or am I going to use the one with the period in it? because they're wanting me to find the speed. I'm going to leave you alone now. You were overcomplicating it, I think, and now you're realizing that's not really the tricky part, right? For v squared over r. Friction is what times what? I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. Johnny. What do I notice? We're on the same wavelength now? I'm probably coming back to you on that little... Okay, you with me? In fact, I get the same expression as we did before. I get V equals the square root of mu ger. Do I know G? 9.8. Do I know the radius? 72. Hey, what's mu? I don't know. What is mu? How can I figure out mu? That's why I split it, because I can't use the 32 here because that's not, they want me to find the speed. Let's repeat this, and I bet you will be able to solve for mu, and then it says that when it's raining, it's half the value, so we'll take this value, divide it by 2, and now we're good to go. This would be a fairly decent written question. It's multi-step. Victor, you got to know your stuff. It's a nice application, because really what we're doing if we're road engineers is we're figuring out what the safe speed sign is that we have to put on this, a few meters before people hit this so they can slow down. Not that people do, but at least then they can't sue us, which really is what those signs are for. It's so that people can't sue the city or sue BC Highways or whatever, right? So we're going to end up with friction equals mv squared over r. In fact, again, we're going to end up with mu mg equals mv squared over r. Hey, Johnny! But this time we're going to get the mu by itself. Okay. How would I get the mu by itself? I guess the coefficient of friction is v squared over ger. It's going to be, when it's dry, the speed is 32 squared over 9.8 times 72. I'll call this mu dry, because otherwise I'm going to get them confused. You get 1.45. I've made up some bad numbers here. This mu technically should be less than 1, I think, and I need to tweak this question. Sorry, I forgot to. But you all get 1.45? Yes? Okay. So I'm going to write 1.45. So mu rain is this divided by 2. 0.725, and I'm going to carry some extra sig figs. You know what? I'm going to use my answer button, but if I wasn't going to use my answer button, I'd probably carry 5 sig figs because I'm using this to find another answer. I would not go 0.726. 0.72562. 0.72562. V is going to be the square root of 0.72562 times 9.8 times 72 times 9.8 times 72, square root of 512, 22.6 meters per second. I would have no problem reversing this question. Here's what I mean. Here, I gave you the speed when it was dry and told you how the coefficient of friction changed. Find the speed when it's wet. I would have no problem giving you the speed when it's wet and the speed when it's dry and asking you to find the coefficient of friction when it was dry. From the speed when it was wet, you could figure out mu and walk over. Something like that. Don't know. Something like that. Next page. So a little technical comment on turning. The reason that friction is inwards has to do with how wheels work. When we turn our front wheels to turn the car, Newton's first kicks in. The car wants to keep going straight. The tread of the tires applies a force to the road at that angle towards the outside of the circle. Forces come in pairs. So the tires apply a force on the road. The road friction applies a force on the car inwards. And we're only looking at the force on the car. It is true there is an outwards force, but it's not on the object that's going in a circle. It's on the object that's pushing me in a circle. So some physicists will say, okay, there is a centrifugal force pointing outwards, but it's on the road. Fine. I'm going to say, let's pretend it's not even a force. There's a force pointing inwards, and on the car itself, it's inertia. So in horizontal circles, the vertical forces are balanced. There's a net inwards force ma, and it's mv squared over r, or it's m4 pi squared r over t squared. And we're not speeding up or slowing down. Unlike that string in the vertical circle where it slowed down at the top and sped up at the bottom. Short-ish lesson. What's your homework? It's also a chance for you to get caught up. Number 1 is good. So this is a top view. If this was a top view, gravity, I guess, would be into the paper. Normal force out of the paper. What force is pulling it in a circle? What? Tension is going to equal MAC. Which, I don't know, it depends whether they give you the period or the, they gave me the period. Tension is going to be M4 pi squared R over T squared. They also want me to find the speed. I can figure that out. 2 is good. 3 is good. 4 is good. 5 is good. Number 5, 13 centimeters. You're going to have to convert that to meters. And I've given you a frequency in revolutions per minute. First, you'll have to convert that to hertz, which is revolutions per second. It's something to do with a 60. And then once you have the hertz, how do I find the period? Take the reciprocal of that, and I'm good to go. 6 is good. 7 is good. 8 is good. 9 is good. So far I've assigned all of them, I know. 10 is good. 11 is good. Skip 12. 13 is good. Mr. Dueck invented a new hashtag for number 14. It says, be careful, don't confuse T as tension with T as period in your equation. Hashtag need more letters in our alphabet. 14 is good. 15 is good. Lots of practice.